Okay, so we're looking at vectors here today. Vectors. Vectors. So let's go ahead and look at the top of page 577. It says the speed and direction in an object moves can be represented by a vector. Notice it said speed and direction. Okay, so what does that mean? Does that mean, so does speed itself have direction then? Does speed itself, so if I'm going, I'm telling you I'm going 50 miles per hour. Do you know where I'm going? Well, you know, right? So this is the difference between speed and the term we call velocity, right? You've heard the term velocity before, right? Velocity. Velocity has a direction. Okay, velocity has a direction. Speed does not. It's just the sheer amount of what you're doing. Okay? It's like if I asked you how much you weigh, okay? If I ask you how much you weigh, and you tell me, well, Mr. Brown, I weigh, I don't know, 160 pounds. Okay? Would I weigh 160 pounds on the moon? Why not? Why wouldn't I weigh the same?
The gravity is different.
Aha. So the gravitational constant is different on the moon, right? Gravitation on the moon is basically about what, 1/6, 1/5 of what we have on Earth. So you would weigh more or less on the moon. You would weigh less, right? Because the moon itself is a smaller object compared to the Earth. So the force that is grabbing you down is going to be less, obviously, right? Because it's a smaller object. Okay, and that's essentially what gravity is, right? Gravity is the Earth pulling you down, right? That's why if I let go of the pen goes down and it never goes up, right? And that's what gravity is, right? Okay. So this weight has a direction. Okay, weight is always being pulled down. Okay, what is similar to this but does not have a direction? You know what that is? I mean, that's speed versus velocity, right? I mean, so weight versus, so weight has a direction. This guy has a direction. Okay, what is kind of the same thing but does not have a direction? This, oh, well, I heard it. Who said what? Mass. Exactly. Mass is what? Mass is just mass, right? It's just there. My mass, okay, is, I don't know. What would it be? My mass is 100 kilograms. Okay. Or I have a mass of just, it's just mass. No matter where I take it to the moon, I'm still 100 kilograms. Okay. Now this is kind of different than what you've heard, okay? Because this is not a good one. This is not a good one. Let's forget about this example. Forget about the kilograms. Let's see. I have a mass of, well, it is kilograms, but I just don't want you to get mixed up. So if I have, let's say I have an object. I have an object, okay, and the object is, the mass is, again, let's say it's 10 grams. Mass is 10 grams. If I take this bar or this thing, whatever, and I take it to the moon, the mass is still going to be 10 grams. Okay. Now there is a corresponding mass measurement in the British unit, okay, that you guys have never heard of. You guys probably never will. Well, maybe you take a physics class. Okay. Somebody go ahead and bring their phone up. Find out what the British unit or the British system unit for mass is. What do you find out? We come up with the term slug. It's a slug, okay? Slug is a corresponding thing to a gram in the, this is an SI unit. Everybody heard about the SI units before, right? Centimeters, kilograms, right? The metric system, right, basically. Okay. So in other words, I can take this anywhere I want to. The mass is always going to stay the same. The weight is going to be different. Because weight essentially is a force, right? And a force is mass times acceleration. Gravitational constant. Okay, we're going off on a tangent a little bit. Obviously, you do not have to know all this stuff. I'm trying to reiterate or trying to let you know what the difference between a vector component and a non-vector component. Okay? Let's remember, vector has direction, and the non-vector, which is actually called a scalar. So the opposite to a vector would be a scalar, is something that does not have a directional component. Okay? So, all right. We spent enough on that. So now let's go back to the book. So speed and direction, right? So if you have speed and direction, it is going to be a vector. Okay. Vector can also be named using component form. So you have an initial point on a vector. All right, and each vector is going to be a head and a tail. Okay, so this will be the initial point. This is called the terminal point. Okay, and that is how you notate a vector. So this will be, if you call this vector V, it is V with an arrow on top. So the arrow on top signifies that this is a vector. Okay, so the vector looks like. So in the context, if I go here, and let's say I started here, and I have a point or vector that looks like this. And this was 1, this was 3, 1, 2, whatever. Okay, so it goes from here to here, right? In order to travel to here, go to here to here, it went how much in the x direction? 2, right? How far did it go in the y direction? Went up 1, right? From 1 to 2. So this vector, if I call this vector A, I would notate it as 2 in the x direction, 1 in the y direction. And instead of using normal brackets, parentheses, I would use this funky looking brackets here. And that again denotes that it is a vector. Okay. If I told you to draw a vector this, and I gave you a starting point of the origin, how would you go? You would go -3 in the x, -4 in the y. This would be your endpoint. That would be your vector. This would be vector B. Okay, we understand how to draw vectors? Okay, all right. Now I could have the same vector starting here, right? If I started here, I could still go over 3 and down 4. Okay. Essentially, they're the same vectors, right? Because it has the same length. It has the same direction. They're parallel, right? It has the same direction. So these essentially are the same vector. Example number 1, write each vector in component form. So the first one is fairly simple. So I'm going a little overboard, as you can see I'm going a little more what the book has. And the reason I do that is because this is one of those things that you will be using fairly extensively when you go to honors calculus, you start taking physics. Okay, these things the vectors are essential. So I'm trying to do a little bit more than just your touch and go thing. Okay. All right. So A, E, F, E, F. So E, F. Look at the book. I'm not going to draw this. How much did it go in the X direction? In the X direction. 4, correct? And then in the Y direction, we went down. So it's a negative value, right? It's negative how much? Negative 3. That's it. Pretty simple. Okay, and B is actually going to give you a coordinate. So you're going to have to trace the coordinates. So you're going from PQ, where P is 7 and negative 5. Q is 4, 3. Okay, so P is 7, negative 5. Q is 4 and 3. So this is P. This is Q. So the vector is from P to Q. From P to Q. How much did I go in the X direction? In the X direction, I started at 7, and then I went to 4. So I went negative 3, right? Negative 3. So in the X direction, it's going to be negative 3. In the Y direction, I went from negative 5 to 3. So I went up how much? 8, right? 8. So that'd be your answer. But this would be PQ. What if I asked you QP? How would that be different? Now I'm starting from here, going that direction. Right? So essentially you would be, right? Because I'm going from here in the X direction over here, plus 3. Then I'm going down 8, right? Because I'm going from here down this way. So you would just basically put in the negatives on both. Did everybody see that? Okay. So you have to be careful with your nomenclature there. When you write something, you can't write it backwards because the vector would be you're essentially switching the starting and the ending points. So it would be an opposite vector, right? So we're going in the opposite direction. All right, example number 1. Example number 2, finding the magnitude of the vector. So basically the magnitude is the length of that vector, right? It's the length of that vector. So example number 2, 4 and negative 2. So draw the vector 4 and negative 2. So I went 4 and down negative 2. So I went start from here, down that way. Any names here? No names. Just like whatever I want. A, so this is 4 and negative 2. So the vector, we'll call this vector P. Vector P is going to be equal to 4 and negative 2. So it starts here and ends up here. Okay, the magnitude is going to be what? Since this is 4 and this is 2, we can just use what? Pythagorean theorem? We do Pythagorean theorem here, right? So the magnitude of the vector are the two bars on the side, okay, not absolute value. This is the magnitude of a vector. Magnitude of a vector is 4 squared plus 2 squared. 16 plus 4. (2√5). Okay, 2√5. Yes, I'm going to ask you to go from here to here in this class. You do not stop here. You can simplify it, you simplify it. Okay? Okay, so that's that. Blah, 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 blah. Example number 3. Finding the direction of a vector. Okay. In the middle there, there's a little blurb there that says direction of a vector is the angle that it makes with a horizontal line. Okay, the angle that is measured counterclockwise from the positive x-axis. Okay, so let's go back to this guy. We just did this one, right? It was 4 and -2. So the angle or direction of this vector is you start from the positive x, going counterclockwise. So it would be that angle. That would be the angle of the vector. Okay. So if I had example number 3, example number 3, the wind velocity is given by the vector 2, 5. Find the angle, I'm assuming this one. Example number 3, 2, 5. So I go 2, up 5. This is the vector. If I wanted to notate where the direction is, again, I start from positive x-axis, going counterclockwise. I'm looking for this angle right here. Okay, so what do I know here? I know that this is 5. I know that this guy here is 2. So if I call this angle x, I know that the tangent of x is going to be equal to the opposite over the adjacent. 2.5. So I go into my calculator to find x. I would say that x is equal to the arc tangent, 2.5. And if I do that, it's 68 degrees, it looks like. 68 degrees, approximately 68 degrees. So that would be the direction of a vector. Okay. Let's go to the top of page 579. Page 579. It talks to you about the equal vectors. We already talked about this. Two vectors are equal vectors if they have the same magnitude in the same direction. For example, in that on the top of your page, the vector u and vector v are the same because it has the same angle, same direction. It has the same magnitude. Two vectors are parallel vectors if they have the same direction or if they have the opposite direction, right? So the one on top, the two same vectors would be parallel vectors, right? Because they are in the same direction. Okay, the one on the bottom one there is that they're opposite directions, but they are the same angle. They're the same, they're still parallel, right? Those are parallel vectors. So example number 4, identify equal and parallel vectors there. So I'm just eyeballing this, right? Equal vectors. Which vectors are equal? Looks like AB and GH are equal, right? Looks like they're the same magnitude, same angle because they go 3 on the x direction and +1 in the y direction. Both of them are the same, right? And then the opposite for the parallel vectors would be CD and EF, because they are this, again, they are parallel lines, they have the same slope, but the magnitudes are different. So they're not the same, but they still are parallel, correct? Okay, so the very last thing that we're talking about is resultant vectors. And I can't even believe that they're going to try to teach you this here at this level. Is this even worth going through? Okay, let's go ahead and do it. So, resultant vector. Resultant vector is if you have two vectors, you can add them together. Okay? And where this comes into play is that when you're doing physics, okay, you have an object. If you have an object that is experiencing not just one force, but several different forces, you should be able to find or calculate the resultant vector of all these forces. That's what we're doing here, okay? So if I have a box, let's make this interesting. Okay, so if I have a ramp, okay, on the ramp, I have placed a box. Okay. What kind of forces are acting on this box? Anybody tell me? It's a box. It has weight, which means that it's going to have, it's going to weight. So weight's going to be pulling it down, right? So you're going to have the weight vector here. Right? What else? Is it moving? Doesn't look like it's moving. Well, then something's got to be counteracting this weight, right? Something's got to be keeping it from sliding down. What's keeping it from sliding it down? Well, I want to slide down. I bet you if I raised the ramp higher and higher, we would fall down, right? But if it's this, I mean, if it's not high enough, it's not gonna, what do we call it when it moves? What do we call that? It is sliding down. So what opposes a sliding force? What is that called? Sliding force. It is called the friction force, right? So you have a force going this way, right? So it's basically friction, right? Because if you were two ice blocks, or, well, not ice blocks, but one was ice and had very, 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 very little friction, it would never stay like this, but it would always slide down, right? But in this case, friction is holding it up, correct? Okay. What else? There's also a force that from this ramp that is holding it up, right? Just like, I don't know, I set this pen like there, right? Is the pen moving? But there is weight that's pulling it down, right? Gravity is pulling it down right now, okay? So there's some force that counteracts that weight to make that it's not coming down. That's holding it up. Okay, and that's a reaction force from the desk. It's holding it up. Okay, in other words, that's this force right here. Okay. So if I add these three forces together, my resultant force should be what? Given the fact that it's not moving, it should be 0, right? Because if there was any leftover force, it would be moving one way or the other. Okay, so this is where we talk about adding vectors, okay? If you go to the bottom of page 579, there are two different methods here that tell you how you can add or find resultant vectors. Head to tail. Okay, so you go head to tail, okay? So basically what you're doing is you are taking this vector And to that vector, you are trying to add a vector that looks like this. So I'm going to add this vector to this vector by going head to tail, and then the resultant vector is going to look like this. Okay, there are two ways to do it. So the first way we did was head to tail, then we go head to tail. That's the resultant vector. The other way to do it is take this vector, I'm going to put it over here. Okay, now I'm going to draw a parallelogram and connect those and say that is the resultant vector. Okay, so those are notated in your little box there, the head and tail method and the parallelogram method. Okay, in other words, they're both trying in the end to find the resultant or addition of the two vectors added together. Okay. So the page on the very top. To add vectors numerically, add their components. So U vector and V vector, if you add them together, they're going to go like what the book said. So if you have a U vector, which is x1, y1, and you have a V vector, x2, y2, then U vector plus the V vector is going to be equal to x1 plus x2, y1 plus y2. So you add the x's together and you add the y's together. Very simple. A kayaker leaves the shore at a bearing of north 55 east and paddles at a constant speed of 3 miles an hour. There is a 1 mile per hour current moving due east. Okay, so what are the actual speed and direction? So the original vector that I am when I am rowing, or the kayaker is rowing, is 55-degree northeast. So starting from north to the east direction, 55 degrees is all what that means, right? So 55 degrees here. So this is 55 degrees, which makes this guy 35 degrees. And the magnitude was what? 3 miles per hour. 3 miles per hour. Okay, so now here's the magic way to do this. So if I call this, since this is the, we'll just call this as vector A. Vector A, what is the x component of vector A? This is the $60 million question. This is, right? I want to know the x component of this vector, because this vector is basically this guy plus the y direction, right? Okay. So the x direction is what? Anybody see that? Anybody see y would be 3 times the cosine of 35? Cosine of 35 is what? Cosine of 35 is the adjacent over the hypotenuse, correct? Right? So the adjacent, whatever this is what I'm trying to find, right? The adjacent over the hypotenuse is cosine 35 degrees. And multiply 3 on both sides. End up with that. Constant will the same by the same method. The y direction is going to be this. Right? Because the sine is the what's the y, right? Sine is going to be the opposite over the adjacent, an opposite over the hypotenuse. Right? That's how that works. But I have to add the effect of the current. The current is going this way, due east, this way, 1 mile per hour. Okay, so if this is the current, we call this the current C. The C vector is going to be equal to 1 and 0, right? Because it's going right here straight this way. It's not going to be in the y direction anyway, right? It's only going to the x direction. So it's this guy and this guy. So the resultant vector, which is going to be A vector plus the C vector, I add the x's up, 3 cosine 35 degrees plus 1. The y is going to be 3 sine 35 degrees. And that's your answer. Does that make sense? This is not easy. If you didn't get this part we just did, don't worry too much. Just realize that there is a method to do it. Okay, remember how to do this. You only need to know how to do this. Okay, so if I gave you two vectors, one is like 3, the other is -6, and here I give you 0 and 8. You should be able to know that u vector plus v vector is going to be equal to 3, 2. Okay, so you should know how to do this. Okay. I don't know that this is example number 5 is anything that you guys are ready. Just realize you should be able to do it. Okay. So what this is actually called, when I go this from here, a vector is from here to here. This is the a vector. We call this the decomposition of a vector. So we're taking one vector, splitting it up to this vector plus this vector, right? You're basically decomposing it because you want to find the x component and the y component. Then you're going to add the x components and the y components together. Okay, call it a day on that one.